Welcome back to the Deep Dive. Today we are taking a look at something we all take for granted, but it's an absolute star of a system. We're talking about human vision.
It really is a remarkable system. I think most people have this idea of sight as a kind of camera, just passively recording the world.
Right.
But as we're about to see, vision is this active, incredibly complex construction, and one that is, well, surprisingly easy to fool.
So our mission today is to go past the basic anatomy. We want to really explore the physics, the biology, and maybe most importantly, the huge amount of cognitive interpretation that happens in your brain every time you open your eyes.
Yeah.
We're really focusing on that surprising, sometimes massive gap between what your eye registers and what your mind is telling you you're actually seeing.
And the sources you provided are perfect for this. They give us a complete picture covering everything from the intricate layers of the cornea to the genetic reasons for color blindness, and even how artists, especially in the op art movement, learn to exploit the weaknesses in our visual system.
It's like a shortcut to understanding your own operating system.
Exactly.
Okay, let's unpack this. Let's start with just the physical engineering of the eye itself. An adult eyeball is what, around 24 millimeters in diameter?
Yeah, that's about right. And what's wild is that a newborn's eye is already, almost 3/4 of that adult size.
Wow. So it's nearly ready to go right from the start.
It's pretty much good to go. And that size is crucial for the optics to work, for converging light onto that tiny spot at the back.
And how that focusing power is split up is, well, it's not what I expected.
No, it's very counterintuitive. Most people think the flexible lens does all the heavy lifting, but actually 70% of the total light convergence is handled by that transparent 5-layer shield at the very front, the cornea.
70%. I always just pictured the cornea as like a protective shield.
It's the fixed powerhouse.
Yeah.
The lens only provides the other 30%, but that 30% is absolutely critical because it's adjustable. And it does this in a really cunning way. The refractive index of the lens, so how much it bends light, it isn't uniform. It's actually a bit higher at the center than at the edges.
So it's kind of a built-in self-correction system to minimize distortions.
Precisely. It's optimizing itself internally. And that flexibility allows for what we call accommodation. That's the process where the ciliary muscle changes the lens's shape so you can shift focus from, say, your phone screen to a tree in the distance.
And we also have intensity control, which is the iris, right? That's the colored part that opens and closes the pupil.
And the aperture control is just phenomenal.
Okay.
The pupil can shrink from 8 millimeters down to 2 in a fraction of a second. That's a 16-to-1 ratio in area.
It's a huge range.
It is. Though, interestingly, the sources pointed out that your pupils are always small when you sleep, no matter how dark the room is.
Huh. Like a defensive resting state.
Yeah.
Now, speaking of wear and tear, we all know that as we get older, focusing up close gets harder.
That's the lens losing its flexibility, that ability to accommodate. It declines throughout your life. It just becomes really obvious when the eye can't bend the lens enough anymore to focus on a book or a screen.
And that's why people start needing reading glasses.
Exactly. Those convex lenses usually happens in the late 40s. And then, of course, there are cataracts, where the protein in the lens starts to coagulate and cloud up.
Making everything look hazy.
Yes, and even before it gets really opaque, the aging lens starts to filter out more of the shorter wavelength light, so violet light specifically. The world can start to look a little bit yellowish. But here's where it gets really interesting. People who have their natural lens removed for cataracts and replaced with a modern one can often get an extended visual range.
Oh, I remember reading about this. You mean they can start to detect light in the near UV spectrum? Light that was totally invisible to them before?
Correct. The natural lens acts as a built-in UV filter. Once it's gone, they gain this kind of hidden, extended vision. It's a side effect of the surgery that basically rolls back a physical limitation.
That is genuinely fascinating. A superpower unlocked by surgery. Okay, so let's move from the focusing part to the detector itself, back at the retina.
The retina is a masterpiece of biology, but it's built in reverse.
What do you mean in reverse?
I mean, the light actually has to pass through this whole network of nerve cells before it can hit the photoreceptors, which are way at the back. And these photoreceptors come in 2 very specialized types, rods and cones.
And the first responders, the ones for low light, those are the rods?
Those are the rods, yeah. They handle scotopic, or night vision. They've got a pigment called rhodopsin, or visual purple. And they are ridiculously sensitive. I mean, they can respond to almost a single photon.
And there are just a ton of them, right? Something like 120 million all over the retina.
Yes, exactly. They give you high sensitivity and a wide field of view, but there's a trade-off. No color, no fine detail. It's why it's basically impossible to read by moonlight, even if you can see the shapes of things around you.
Right. And in bright light, the rods are useless. They just get saturated. It takes about 30 minutes in the dark for them to get back to full sensitivity.
That's your classic dark adaptation. And that crucial rhodopsin pigment, its synthesis requires vitamin A. A deficiency causes night blindness. This little biochemical fact actually became a national security asset during the Second World War.
Ah, the carrot story. This is one of the best anecdotes. The Allied night fighter pilots were suddenly becoming incredibly effective because of new radar systems.
Secret radar systems. And to keep the technology a secret, British intelligence cooked up one of the most famous pieces of misdirection in history.
They did. They publicly said that the pilots' amazing new effectiveness was because they were eating huge amounts of carrots and cod liver oil.
And it worked perfectly, because the underlying science, the vitamin A link to night vision, made the whole story sound completely plausible.
An intelligence coup disguised as a health tip. Okay, now let's switch gears.
Yeah.
Bright light, sharp detail. For that, you need the cones. Photopic vision.
Cones are the complete opposite of rods. They're less than 100th as sensitive, but they're what give you color and your highest visual acuity. And they're mostly packed into the fovea, that little spot right near the center of the retina.
The fovea is the high-res zone, packed with, up to 200,000 cones per square millimeter. Let's talk about acuity. What does 20/20 vision actually mean?
Normal visual acuity, or 20/20, means you can resolve detail down to about 1 minute of arc. To put that in real terms, imagine you're lining up a golf putt from less than 3.5 meters away.
Okay.
At that distance, you could actually notice if the ball was nudged by just 1 millimeter.
That's incredible resolution.
It is. Under the best conditions, your eye can even spot something as thin as a 0.1 millimeter wire from 20 meters away. Our ability to see boundaries is just stunning.
So how do those cones let us decode color?
You need 3 types of cones, and each has a different light-sensitive pigment called an iodopsin. So you have short-wave, mid-wave, and long-wave sensitive cones.
And this is where the naming gets a little tricky, because the cone we call red sensitive doesn't actually peak in the red part of the spectrum at all.
That's a huge point of confusion. The red cones, the long-wave ones, peak in the yellow part of the spectrum. The green ones, mid-wave, peak in the green. It's only the short-wave cones, the blue ones, that are roughly where their name says they are.
And there are fewer of those blue cones, right?
Way fewer, less than 10% of the total.
Hmm.
And they're especially sparse right in the center of the fovea.
But why would the spot for the sharpest vision just skip the blue cones?
It's a brilliant trade-off. It's physics. Because the eye's lens bends different wavelengths of light slightly differently, you can't get perfect focus for all colors at the same time.
Right, chromatic aberration.
Exactly. So by focusing on that narrow band between green and yellow in the center, you get a much sharper, better compromised image overall.
So we sacrifice a little blue precision for much higher resolution.
Yeah.
That completely reframes that standard optometry test for reading letters on red and green backgrounds.
That test is directly targeting that. It's helping find the best compromised lens for that crucial yellow-green zone where your sharpest vision happens. The whole visible spectrum is actually pretty small anyway. It's about a 2-to-1 ratio in wavelength.
Binary.
Human hearing spans over 10 octaves. That's a 1,000-to-1 ratio. Our visual range is tiny by comparison, but the perception of color within it feels infinite.
And when that perception breaks down, we get color blindness, or Daltonism, as it was first called.
After John Dalton, the chemist who was colorblind, Thomas Young figured out the cause way back in 1802, the absence of one of the 3 types of cone. And the most common form is red-green color blindness.
And this is where the genetics comes in. It's linked to the X chromosome.
Absolutely. The genes for both the red and green sensitive cones are right there on the X chromosome, and their DNA sequences are so similar that they're just really prone to errors during cell division.
And the most common error is?
Deuteranopia, the lack of green sensitive cones. It makes telling the difference between anything in the yellow to red range extremely hard.
And because men only have one X chromosome, they're much more likely to have it. What are the numbers? Something like 7.7% of Caucasian men.
Compared to just 0.6% of women. That sex-linked inheritance explains it all. By contrast, the gene for the rare blue-sensitive issue, tritanopia, is on chromosome 7, a non-sex chromosome, so it affects men and women about equally.
And the most extreme case is achromatopsia. No cone function at all, just seeing in shades of gray.
It's incredibly rare globally, but it's highly concentrated in a few isolated populations, like on the Pacific island of Pinjalap. There, it affects about 1 in 12 people, a powerful reminder of how fragile this whole system is.
So let's follow those signals from the retina to the brain. The nerves from both eyes meet at the optic chiasma, and there's a crossover.
Yes, and this anatomical crossover is absolutely critical. The information from the right half of your visual field, which hits the left side of both retinas, all gets sent to the brain's left hemisphere, and the opposite for the left field.
So the visual world is split cleanly in two for processing.
Right. And once that data hits the visual cortex, the brain is just constantly compensating. It has to. The most obvious example is the blind spot.
Where the optic nerve leaves the eye, so there are no receptors.
We should all have this gaping hole in our vision, but you never notice it. Why? Because the brain just fills it in. It confidently guesses what should be there based on the surroundings.
It makes you wonder how much of what we see is actually just the brain inventing a plausible reality.
Well, exactly. And it does this for more subtle things, too, like Haidinger's brush, which is about polarization. If you stare at a blue surface, you can sometimes see this faint mustard yellow bow tie shape.
I've heard of this.
It's real, but it only lasts for a few seconds before the brain just compensates and makes it disappear.
This idea of compensation is also at the core of movies, right? Persistence of vision.
Absolutely. Your cone cells take about 50 milliseconds to recover. So movie cameras running at 24 frames per second use a double shutter to flash the screen 48 times a second. It's too fast for your cones to keep up, so the visual cortex just fuses it all into smooth, flicker-free motion.
The time delay is also key to one of the most fun optical illusions, Pulford's pendulum.
Yes. If you watch a pendulum swinging back and forth, and you can dark piece of glass over one eye, the straight line motion suddenly looks like it's tracing an ellipse.
So what's happening there?
It's simple, really. The dark filter reduces the light, so the signal from that eye takes just a little bit longer to get to the brain. The brain gets two conflicting location reports at the same instant.
And to make sense of that time lag, it invents a third dimension. It assigns the pendulum a position that's farther away or closer, creating a 3D path to reconcile the two inputs.
The brain will choose a consistent, even if it's a completely manufactured reality every time. This brings us to geometric illusions, which tell us a lot about how the cortex has learned to interpret things.
Like the classic Miller-Lyer illusion. Two lines, same length, but they look different because of the arrowheads. And the sources say this is almost certainly happening in the visual cortex, not the eye.
What's so fascinating is that people who grew up in cultures without rectangular architecture, they don't experience the illusion as strongly.
So it's a learned cognitive habit. Our brains are so programmed to see right-angled corners in 3D that it tricks us.
It's a great example of that. And then you have things like the cafe wall illusion, where perfectly straight parallel lines look like they're tilted.
That one is baffling.
It all comes down to the contrast and thickness of the boundary lines. It tricks your brain into seeing angled wedges where there are none.
But the ultimate compensation trick has to be color constancy.
Oh, absolutely. It's a survival necessity. Your visual cortex is constantly adjusting for huge shifts in lighting. A white piece of paper looks white in bright daylight, and it still looks white under the very orange glow of a candle.
The brain just corrects the color balance automatically.
It has to, otherwise the world would look completely different every time the lighting changed.
Okay, one final fitting illusion. Benham's disc. It's just a black and white disc, but when you spin it, you see colors.
Faint colors, yeah. A grubby little rainbow. This is because the three types of cone, especially the blue-sensitive ones, they all react and recover at slightly different speeds. The rapid flicker of the black and white patterns hits those different recovery rates just right, and it generates a false perception of color.
What a journey. I mean, we started with the pure mechanics of the cornea, and we've ended up with our brain just making up 3D movement and inventing colors to keep our reality consistent.
And that's the key takeaway for you. Vision is not a recording. It's an active, complex, and often compensatory story that your brain tells itself. All those tricks, filling in the blind spot, maintaining color constancy, they're all essential for building a stable, functional world.
And that construction, that's what artists exploit. You mentioned op art. Artists like Victor Vasarely and Bridget Riley, they use these sharp geometric patterns designed specifically to mess with these systems.
They knew they could tap right into the system's predictable weaknesses. They could force the brain to see movement and shimmer where none actually exists.
So if we connect this all the way back to how your eye physically works, when you stare at any still image, your eye is never truly still. It's always making these tiny involuntary movements, flicks, drifts, tremors.
Those movements are essential. They're what allow the receptors to keep refreshing. Without them, the world would just fade into a uniform gray.
So this raises our final provocative thought for you to explore. If OpArt is designed so that the pattern spacing interacts with those tiny repetitive eye movements to make the image appear to flicker or vibrate or wriggle, what does it mean that your own natural involuntary eye movements are the catalyst that allows a still image to appear to move? Is movement an inherent function of the act of staring itself? Keep that in mind the next time you look at anything truly still.